Alright, this will be the last of the Unit 4 videos, this one on isotopes. It's important that we know what isotopes are and that we can deal with these isotopes in terms of their atomic structure, being able to find protons, neutrons, and electrons in these substances. First, we'll go into what they are. Isotopes are atoms of elements that have different atomic masses. When we start talking about the periodic table over here, we're talking about the average atom of an element. They take all the known forms and they calculate a weighted average for its mass. And so the masses you find on the periodic table over there represent the average atom of the element. That is only one possible form. For every element on the periodic table, there is more than one possibility. When we look at these groups of atoms together, all these different atoms and their different masses, we're talking about the isotopes of that element. The reason why these atoms have different masses is because they have different numbers of neutrons. The neutron is the neutral particle in the nucleus. It's the atomic glue that holds the nucleus together, keeps those protons from repelling each other. Some atoms of an element have that typical number of neutrons that the periodic table says they should. Some have more, some have less. They are still the same element because they have the same number of protons. Protons are for identity. Protons determine the atomic number. Protons determine what it is. They all have the same number of protons, so they're all the same element. But they have a different number of neutrons. Some are heavier, some are lighter than others. It's kind of like people. Some people are really skinny and really light. Some people are average. Some people are larger than average. They're all still people, though. We'll take a look at a couple of examples. These are the three isotopes of hydrogen. Hydrogen atomic number 1. First element on the periodic table. It's got 3 different isotopes, or 3 different possible forms. This one represents the typical atom, the one that's on the periodic table. 1 proton, 1 electron, that's it. No neutrons. The mass of this particular atom of hydrogen would be 1. This is deuterium. What makes deuterium different is that neutron that it has. It has a neutron in the nucleus, so the mass of this particular isotope is 2. This is tritium. This is the 3rd isotope of hydrogen. And again, what makes it different is that it has 2 neutrons in the nucleus, so the mass of this one would be 3. They're all hydrogen, and the reason why they're all hydrogen is because they all have 1 proton. If you have 1 proton, your atomic number is 1, you are hydrogen. They're all hydrogen, but what makes them different is their mass. This is the lowest mass, this is the highest mass. Again, it's kind of like people. This is the skinny hydrogen, that's the heavier hydrogen. These are the isotopes of helium, and there are 4 of them. Again, same principle, they are all helium, and because there are 2 protons, their atomic number is 2. Look it up on your periodic table. If your atomic number is 2, you are helium. Every one of these are helium atoms. What makes them different is the number of neutrons. This one has 3 neutrons. Combine that with the 2 protons, its mass is 5. This one has 4 neutrons. Combine it with the 2 protons, its mass is 6. This one has 5 neutrons. Again, combine it with those 2 protons, mass is 7. This one has 2, 4, 6 neutrons. Combine it with the 2 protons, its mass is 8. Again, it's just a difference in the number of neutrons. It's a difference in their mass. Now, some of these will have more stable nuclei than others. Some of these are very stable nuclei. They'll stick around forever. They'll never break down. Some will be unstable. Sometimes they don't have enough neutrons. And when they don't have enough neutrons, there's not enough glue to hold that nucleus together. That nucleus falls apart. Sometimes they have too many neutrons. It's like building something with wood. If you put too much glue in a joint, it makes that joint unstable. If we have too many neutrons in a nucleus, sometimes that will make it unstable. and that nucleus will fall apart. So while they are the same element, and they will react the same way that every other atom does, we may see a difference in terms of how stable their nuclei are. Isotopes have their own specific types of symbols, and these symbols are written to show us what the mass of our substance is, what our isotope is, directing us towards a specific atom. Instead of the typical one the periodic table gives us, using an isotope symbol allows us to refer to a specific form of that atom. You write the symbol of the element, whatever that symbol may be. In the upper left-hand corner, you put the mass number, the number of protons and neutrons that that particular isotope has. You put its mass on top. Underneath that, you write its atomic number, its number of protons. So symbol, top left is the mass, bottom left is the atomic number. So I'm just going to real quick do the symbols for these three isotopes of hydrogen. Again, it starts with their symbol in all cases. The symbol for hydrogen is H. The number that goes on top is the mass, the total number of particles in the nucleus. Protons plus neutrons, the mass of this is 1. And then underneath that we put the atomic number, the number of protons, 1. Over here for this hydrogen, again, same principle. Start with the symbol for the element, H for hydrogen. On the top we'll put the mass, the total number of particles in the nucleus. Protons plus neutrons. There are 2 of them. And underneath that, the atomic number, which again is the number of protons. There are 1 proton. There is 1 proton in that nucleus, so the atomic number is 1. Again, you can see the difference. The difference is mass. Last one on here, the tritium. Again, start with the symbol H. On top, we put the mass, which is the protons plus neutrons, or total number of particles. There are 3. And underneath that, the number of protons, or the atomic number, is 1. So again, you can see that all 3 symbols do have a couple of things in common. They all have the same symbol. They all have the same atomic number. What makes them different from each other is the mass. We can do the same thing for the helium, and the symbol for helium is He. So for every one of them, same symbol, He. Number that goes on top is the mass, that is the total number of particles. 1, 2, 3, 4, 5 for this one. The number that goes on the bottom is the atomic number, or number of protons. There are 2 of them. Again, the number that goes on top is the mass, that's the total number of particles. 1, 2, 3, 4, 5, 6, 7. The number that goes on the bottom is the number of protons. 2. Again, the number that goes on top is the total number of particles, or the mass. 1, 2, 3, 4, 5, 6. The number that goes on the bottom is the number of protons. And there are 2. And finally, again, on the top is the mass. The total number of particles. 1, 2, 3, 4, 5, 6, 7, 8. The number that goes on the bottom is the number of protons, and there are 2. So once again, we can see the symbols and the atomic numbers are all the same. What makes them different is their mass. Now, if you're presented with one of these isotope symbols, you have to use the information that's given to you to find the subatomic particles. Protons will still be equal to the atomic number. We don't do anything different there. They are the same elements, so they will still have the same number of protons. The electrons will still be equal to the number of protons. We're still dealing with those neutral atoms. For the atom to be neutral, the protons and electrons have to be the same. The only difference is the number of neutrons. When we find our neutrons, we have to use the mass that I give you. You have to use the mass from the isotope symbol. You ignore the periodic table. In fact, when you have a symbol like this, you don't even need the periodic table to do this. You have all the information that you need right here. This is carbon-14. To find the number of protons, all we need is the atomic number. We could go to the periodic table to get it, but it's right there. So there's no reason to. 6 protons. And electrons and protons will still be the same. So we can assume there are 6 of those. This is a neutral atom. For the neutrons, ignore the table. Use this mass, the 14 that I give you. You take 14 minus 6. There are 8 neutrons in this particular carbon atom. If you went with the periodic table would tell you 6, and that would be incorrect for this one. Again, use the mass that I give you when working with your isotopes. I'll do one more example. This is calcium-48. Again, we don't even need the periodic table for this one. Protons are atomic number. It's the number on the bottom. No need to even look that up. Electrons will still be the same as the number of protons because this is still a neutral atom. The neutrons, again, ignore the table. Go with the information I give you. You have to use this mass, the 48. Take the mass minus the atomic number, top number minus bottom. 48 minus 20 is 28 neutrons. Again, the key here is just to ignore the periodic table when these numbers are written to the left of the symbols. One last thing, you might see isotope names. And the isotope name will also include that mass. This is carbon-14, so when we write the name, we write carbon-14. The mass is written after the name, so we know which one we're looking at. This is calcium-48. Again, when we write the name, we put that 48 on the end so that we know specifically which one we're talking about. That's it for Unit 4. If you have any questions, post them to the wall or ask me sometime during class.